Chapter 12, Auditory Localization and Organization. Now, the reason this chapter is really important to me is because this is going to cover some of the fundamental problems or some of the fundamental issues and challenges that we have in trying to understand how we do complex things that don't seem complex, but they really are. For example, if you look at this scene right here, and if you look at, let's say you picture yourself, you're in a Starbucks or you're in this coffee place, and you hear a bunch of different sounds. You're listening to somebody talk. You've got sound bouncing around off of different You've got sound bouncing around off of different places, other conversations going on. You've got music bouncing around in the background, and the music and the sounds that are bouncing off of the walls and off of the floors are giving you a lot of information about the size of the room, how many people are in it, what the walls are made of, what the floors are made of. And then you've got the ability as well to hear when somebody mentions your voice, or I'm sorry, somebody mentions your name. So in all this mix, if somebody calls your name, you're going to be able to pick that out, and you're going to be able to hear it. So if they say, "Hey, Ray, your coffee is ready," or "Your latte is ready," or whatever, you'll be able to pick that out from all of this, and it's a very interesting set of problems, a very interesting set of challenges as to how it is we're able to localize where things come from, sound wise, how we're able to localize that. And that's going to be the topic of this particular chapter. So, one of the concepts you need to understand in dealing with auditory localization is that of auditory space. And basically, the auditory space is the sounds that surround a particular observer. So, wherever you happen to be sitting, you're always going to be in this auditory space. Um, we do research on how to localize sounds according to how we're able to pinpoint the coordinates as to where they come from. So the coordinates that we use in identifying where people think sounds are coming from break down to the following. If you've ever learned how to shoot a missile, um, across the air, these will sound familiar to you. The first one are the azimuth coordinates, and these are the coordinates going left to right. Right, so all the way from 0 degrees to 90 degrees to 180 degrees, all the way back to 0 degrees. Right, the coordinates around you, left to right. And then there's the elevation coordinates, the coordinates up and down, all the way from flat 0 degrees to a 45-degree angle to straight up shot 90-degree angles. That's the elevation coordinates. And then the distance. How far away do you think a sound is coming? If it's coming from a far distance or from a close distance. So if you think about that, if you put these three things together, if you put left and right, up and down, and distance, these three coordinates together will allow you to identify a point in space where you think a sound is coming from. And this is something that we are typically pretty well able to do. So here's a picture, right? This person giving you the illustration of what these coordinates look like: azimuth, elevation, and distance. Um, we are best at localizing sounds that are right in front of us. That's because we're using both our ears. If we have both our ears and we're facing the front, we're really good or pretty good at localizing sounds. The sounds that come from behind us or to our sides, we're least accurate about that. Mainly because obviously your ears aren't behind you, right? Your ears are designed to pick up sounds in front of you. if they're coming from behind, you're going to get less information and you're going to be less able to tell where the sound is coming from. Also, to the side as well. If a sound is coming from the side, you're only going to hear it with one ear, and you're going to have a tougher time determining, for example, how far away it is, or exactly where it is in relation to left and right on your azimuth. Um, Here's the really interesting thing about auditory localization, and this is distinct from um, vision, right? Localizing vision, because whenever you have like a visual stimulus projected onto your retina, there's information on the retina to tell you how close one thing is to another thing, right? So if you're looking at a dog standing next to a tree, you see the retina, the image projected onto the retina has the tree and the dog, and our brain is able to use that basic information to calculate the distance between the dog and the tree, or how far away you are from the tree. That information is not contained in the receptor cells for audition. The only thing that we're getting for auditory stimulation is the vibration of the sound traveling through the air. We have to calculate, taking in the different sounds coming to our ears and their pitch and their intensity and all the other things that we're going to talk about. We have to calculate where things are coming from based on the simple vibrations of receptors inside of our ears. So it's a very different problem from vision, in that we are actively calculating based on the data that comes in, a guess as to where things are located. So, for example, if you're looking at this kitty cat and a bird on a tree, your visual system tells you right away, based on the information that's going to your retina, where the cat and bird are relative to each other. You can see that immediately. But if you're just listening to the tweet tweet and the meow meow coming from the kitty and the bird, you cannot tell specifically where they are relative to each other. You know that you can tell that they may be close to each other, um, but there's no real information there in in the actual stimulus itself, in the sound stimulus, that where the tweet and the meow are coming from. They vibrate your ear all at the same time. They vibrate right here. They vibrate the inside of your ear, the cochlea, all at the same time. So we have to calculate. Rather than seeing two separate objects here, a bird and a kitty cat, we have to calculate that, yes, there's two separate things over there. There's a bird and a cat, and I believe they're located close to each other based on the way the sound is coming at me. We have to calculate all that. It's not readily apparent from the vibrations of the ear. There are a lot of different cues that we use to calculate and localize sound. One of the types of cues that we use are called binaural cues, and these are cues that are based on the comparison of the signals received by the left and right ears. One of the one of the binaural cues that we use is called the ITD, or the interaural time difference, and this is the time difference between the times when the sound reaches the two ears. Right? So if the sound reaches both ears at the same time, there's no difference in time, and that means what's probably happening is the sound is right in front of us. If the sound reaches one ear prior to the other ear, we calculate that that sound is coming from the ear that heard the sound first. So if I hear a sound first here in my right ear, and then a few milliseconds later I hear it in my left ear, I'm going to know, my brain is going to be able to calculate that that sound is probably coming from off to my right. Only because of the physics of our head, of course, right? I mean, if the sound is coming directly at us, it's going to hit both ears at the same time, and we'll know it's in the front. But if it's coming from the side, it'll take longer to hit this ear here because it's coming from this side, because the sound has to go. The sound that you're hearing is not coming directly from the stimulus; it's bouncing around, and coming off of surfaces or whatever, and then bouncing back into your ear. So there's going to be a delay. Um, Another binaural cue, in other words, a cue that requires both ears, is the interaural level difference, the ILD. And this is the difference in the sound pressure level reaching the two ears. In other words, um, which is louder, right? Is this one louder or is this one louder? Um, for very high frequency sounds, intensity happens a lot for the far ear. So if I'm listening to a high frequency sound, like a high pitched scream or something, and I'm listening to it from my right side, it's going to be much louder in my right ear because it's coming from the right side than it is from the left ear. High frequency sounds get knocked down a lot more in intensity than low frequency sounds. If you've ever heard a low frequency sound, like a thumping bass in a car, those annoying people that have those annoying basses, it seems to come from everywhere. That's because you don't have this phenomenon where the low intensity sound is reduced because of this acoustic shadow that your head casts. In other words, your actual head absorbs the high frequency sounds much better than it absorbs low frequency sounds. Um, and since it absorbs high frequency sounds, when it absorbs those sounds, there's less sound that's passing past your head to go off to the side. So there's a much greater difference in intensity for high frequency sounds than there are for low frequency sounds. For low frequency sounds, it passes right through your head because of the distance of the frequency. It passes right through your head. So that sound is traveling everywhere. It passes through your head, bounces off of something, and hits your head again. So you don't get that reduction in intensity. You still hear the boom, 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 no matter what. Um, here's the reason why. High frequency sounds have a much smaller spacing in the wavelength than the large frequency sounds do. And since the high frequency sounds have a smaller spacing, the spacing of high frequency sounds is smaller than your head, right? So here's your head. So since they're smaller than your head, as the high frequency sounds pass by your head, some of them get absorbed. And you end up with what's called here this acoustic shadow right here, where there's no high frequency sounds that can affect your hearing. As a result, a high frequency sound like a 6,000 hertz tone is going to sound much louder on the side it's coming from than the opposite side, only because of this acoustic shadow, because of the disappearance of some of the sound because of your head. Low frequency sounds have very large distances between their wavelengths. As a result, they don't get affected by your head because they're so big that they basically skip right over your head. Most of them skip right over your head as they pass your body. As a result, all of this energy flows right over your head and then gets bounced around and is available for your ears to pick up. Um, Here's an example of this phenomenon: the interaural level difference. In other words, the difference that we have going from just 10 degrees off from the center of our of our front view, all the way to 90 degrees, which is off to one side of your head. And if you look here at you have these three different sources of sound. One coming from almost directly in front of you, one coming from a 45-degree angle, and one coming from one side of your head. And they're represented here by these lines on this graph. And the higher on the x-axis we go in on this graph, the more difference there is between the left ear and the right ear. And then the higher we go here on the on the y-axis, and then on the x-axis, the higher we go here on the x-axis, the higher in frequency. As you can see, the higher we go in frequency off to the side, the higher we go in frequency off to the side, creates a huge difference in the decibel level between the left ear and the right ear. So by the time we hit, let's say, 5,000 hertz, which is a fairly high frequency sound, by the time we hit 5,000 cycles per second or 5,000 hertz, and the sound is coming from either our left or from our right. In this example, it's coming from our right and hitting our right ear. The difference between the intensity in the right ear and the intensity in the left ear is almost 10 decibels, like about 9, maybe 9 decibels, or just over 9 decibels it looks like. And that's a big difference. Notice that's only for the 90 degrees, right? If we look at the 10 degrees, we still get the effect, right? But it's not as intense. And of course, with the 45 degrees, it's in the middle. It's in between the 10 degree and the 90 degree. And this is a great illustration of this phenomenon of the interaural time difference and its relationship to where the sound is coming from and the frequency that you hear things. This is why sirens, ambulance sirens, and police car sirens, this is why they're high pitched, because we're better able to localize a high-pitched sound than a low-pitched sound. Low-pitched sound, it just sounds like it's coming from everywhere. But the high-pitched sound, you can tell where it's coming from much easier. So one of the tasks that you see here on this figure is from your book. The previous figure was figure 12.6 on page 293. This right here is figure 12.7, and this represents the cone of confusion, right? We're able to tell differences only if they are a bit far apart. In this example here, we're going to have a really tough time telling if a sound came from point A or point B only because they are way too close apart. And they're way too close to each other. Okay, with our ability, with our ears, the way they're designed, with our hearing system, the way it's designed, it's a lot easier for us to tell the difference between point A and point B. Say if point B was here and point A was coming from up here somewhere. But this little area, this little spot emanating from our ear and where the sounds can be close together is referred to as the cone of confusion, because we confuse where sounds are coming from.